Greetings out there in calculus land. It is a good day. We're going to talk about parametrics and how they relate to calculus. We did parametric equations yesterday, just a reminder of what they were, or if it was the first time you had seen them, an introduction to what they are. And a reminder is that they are a set of equations that relate to a parameter, which we generally call t, but not always. So how does an x and a y component on a graph get affected by a third variable? So how does that fit into derivatives and integrals? We're basically just going to study two topics, really derivatives, where we talk about just the slope of a tangent line and concavity. And specifically for integrals, we're going to talk about the length, an arc length. First of all, what is the parametric form of a derivative? Well, you guys know the derivative, just the derivative in general, is dy over dx. That's the basic variables that we were using. These equations are related to in terms of t. So it's x of t and y of t. So in essence, all we're really doing is taking the derivative of y with respect to t over the derivative of x with respect to t. So a first derivative is pretty simple. You just take the derivative of y and the derivative of x. You have a ratio, simplify it if you can, you're all done. Now it's a second derivative that's interesting. Because if you remember this notation, the notation by Leibniz, the dy over dx. So if I have a derivative, and I want to take a second derivative, then really what am I doing? I'm taking the derivative of this thing with respect to x again. Now that's the reason why the notation looked like this. Wonder why it was d2y over dx squared? Because really the derivative is twice, the function is once, and there's two dx's. That's the reason for that particular notation. Now the notation is going to help us find a second derivative of a parametric equation, because we're going to do a little bit of manipulation with this. Because you have to remember, in a parametric, the dy over dx is really defined as this, right? So it's really dy over dt over dx over dt. Now that is a lot of d's, okay? But if we do a little rearranging to this, here's what we're going to find. We're going to take the derivative with respect to t. Alright, so this dt and this dt are the same. This dy and dx are going to be in here. Alright. Over, what do we have left? Dx dt. So that's these. Alright, so when we kind of just write it all out, here's what we're doing. To find a second derivative, we are taking the derivative with respect to t of dy dx, which is really what we did over here, over dx dt. Alright, let's see how that's used, and maybe it'll make more sense. Alright, find the slope and concavity. So the slope and concavity, of course, we need to find a first and second derivative. So first derivative, remember it is dy over dx, and dy, remember, is dy over dt. So what is, we'll put it out there just to make sure that we keep everything straight, over dx over dt. That's why this Leibniz notation is actually really good, better than y prime. I know it's a pain to write all the time, but it makes the ratios flow better. You can see what these dt's would cancel out and be left with dy over dx. So what is dy over dt? The derivative of y with respect to t? Well, it's just 3. And what's the derivative of x with respect to t? We'll get the square root of t, so it's 1/2 t to the negative 1/2. Dual simplification, we get 6t to the 1/2. That's the derivative. That's dy over dx with respect to t. In this particular case, we're asked to find the slope when t is 1. So if I evaluate this at 1, I get 6. So the slope is 6 when t equals 1. Now concavity, we're going to need a second derivative. All right. So to find a second derivative, remember this is what we do. Okay, we're going to take the derivative of this. Okay, what's the derivative of 6t to the 1/2 power? Well, it's 1/2 6t to the negative 1/2 over dx dt. Remember, we're taking the derivative of the function we just took over the derivative of x with respect to t. Well, dx dt, remember, is this. It's 1/2 t to the negative 1/2. So if you think about it, what you're doing is you're taking the derivative of the derivative, which is that. That's the numerator. And your denominator is dx dt. That's the second derivative for a parametric equation. Now, it just so happens in this particular case, the 1/2 divide away, the t to the negative 1/2 divide away, you're left with 6. So your second derivative is just 6, which means it's concave up. All right, let's try another one. This time our parametric equations are to find x equals cosine and y equals 3 sine. So the first derivative, take the derivative of y with respect to theta this time. So the derivative of y would be 3 cosine theta, because derivative of sine is cosine. The derivative of x is negative sine of theta. If you can plug in 0 for theta, you're going to realize that you're going to get a 0 on the bottom. So our slope is actually not defined at 0. All right. I'm just going to rewrite this to make it a little bit easier to take the next part. So this is just cotangent. All right. So the second derivative So the derivative of negative 3 cotangent of theta, remember the derivative of cotangent is negative cosecant squared. So this is going to become 3 cosecant squared of theta over our dx dt, which is negative sine of theta. Now, remember cosecant is just 1 over sine, so this whole thing becomes 3 over sine cubed. Now when I plug in 0, guess what? It's undefined again. So it is neither concave up or concave down. At 0. That's kind of a bummer of a question. Like, hey, all this work for nothing. Well, that's not nothing. We know that the slope is not defined, and we know it's not concave up or concave down. But we do know our first derivative is this function, and we do know our second derivative is this function. Right, there you go. Derivatives with parametrics. Now let's take that and find a tangent line. Tangent line to this parametric equation right here, this pair, this set. So of course we need a slope and a point. So our slope, let's do it, dx over dt. So the derivative of y with respect to t is negative t to the negative 2, right? That's t to the negative 1, good. And the derivative of x, in this case, well, that's just 1. Well, that's nice and easy, because we're going to evaluate this at 1 when t equals 1, so our derivative would be negative 1. or should I say our slope is negative 1, our derivative is this. Our derivative is this function's slope is negative 1. Well, now we need a point. Well, I know that at 1, we're going to get 1 minus 2, or negative 1. When I put 1 in for y, I'm going to get 1 over 1 plus 3, which is 4. So I have my point, 1, 4, my slope of negative 1. I should say my point was negative 1, 4. My slope is negative 1. So there's the equation of my tangent line in point slope form. But since this one looks pretty easy, we're just going to do that and call that the equation of the tangent line when t equals 1. That's how we do it. That's it. Last example we're going to do is arc length. Now you guys remember distance formula. And we've done arc length before, but not at parametrics. But I want to show you they kind of make more sense almost with parametrics. So in the distance formula, yay, this one, x2 minus x1 squared. Whoops. I don't know where that came from. y2 minus y1 squared. All right, now, change of x, change of y. That's really all that it was, wasn't it? How did the x's change? This was the distance of a straight line. The x's changed how the y's changed, and it's Pythagorean theorem. Okay? Now, how do we do arc length? Well, so we call it an L, because it's different. And the idea is, it's calculus. We're having infinite amount of lines. We're taking a smooth curve. Remember, we're taking a point, and we're just seeing how long that line is. How long that line is. How long that line is. And we're going to add a whole bunch up. And obviously, the more lines, the better. So we're going to add an infinite number of lines. Hence this. But I want you to think about it. If you have a parametric, remember, x's and y's are defined as another variable of t. So your distance of x is just defined as this. And your distance of y is defined as that. This is your arc length formula. If you remember the arc length formula we used before, it's very similar, except we had a 1 plus dy over dx, or dx over dy, depending on how we did it. Okay? Because we had to have one function here, we can use the two functions because we have a parametric. Anyway, very easy application. Let's find the length of this smooth curve. So the length goes from 0 to 3. We're going to take the derivative of this, which is going to be 6t, square it, the derivative of y, which is 5, square it, take the integral with respect to t. Now you guys know how to take integrals. This is not right now about how you do integrals. In fact, I made this problem up, so I don't even know if you can take the integral of it. So I'm just going to throw this, I already did, I'm going to throw it into a calculator, and I'm going to get this answer. It's approximately how long that line is. That's arc length, and that is all you need to know for parametric equations and their relations to derivatives and integrals. And there's more. There's more calculus. You can find the area under the curve, and you can rotate them and get volume, but those are not things that are important for right now. It's just the first, second derivative and finding a length. So hopefully you found this informative, and I will see you later.